In this video, we have to see that what is the form of standard and canonical form of LPP, that is a linear programming problem. First, we have to see that what is the general form of linear programming problem. For this purpose, we have to take n variables x1, x2, etc., xn. Then we have to specify the objective of the function, that is we have to specify maximize or minimize. Then the objective function of the LPP is denoted as by z. Z equal to c1 x1 etc. c2 x2 etc. cn xn, subject to the constraints. The constraints is of the form where either less than or equal to or equal to or greater than or equal to type, and also it also noted that non-negativity restriction, that is the variables are non-negative. Next, we note that some of the constraints may be equalities or inequalities. Inequality means that is less than or equal to or greater than or equal to type, or all of them same type, that is if all of them are less than or equal to type or greater than or equal to type. Then we have to know the definition of solution, that is a set of values x1 x2 etc. xn which satisfies the constraints of the LPP is called solution. Then if the solution which also satisfies the non-negativity restriction of the LPP is called as feasible solution, which this feasible solution which also optimizes, that is optimizes means maximize or minimize of the objective function of the LPP is called optimum solution or optimal solution. Next, before going to know about the standard and the canonical form of LPP, first we have to see about the definition of slack variable and surplus variable, and what is the use of slack and surplus variable. Next, for first we have to see about slack variable. If constraints of the LPP is of the form sigma I equal to 1 to n etc. ai xi less than or equal to bi, that is constraints is or all of the constraints is of the form less than or equal to type, then the non-negative variables si which are introduced to convert these inequalities to equality is called as slack variable, that is sigma I equal to 1 to n aij xj plus si equal to bi, that is less than or equal to is converted into equality by adding the slack variable. Similarly, the definition of surplus variable is of the form, that is if the constraint of the LPP is of the form, that is if the constraint is greater than or equal to type, then the non-negativity variable si which are introduced to convert the inequalities, that is the greater than or equal to type inequalities to be converted by subtracting the variable si. That si is called as surplus variable, that is sigma j equal to 1 to n aij xj minus si equal to bi, that is greater than or equal to constraint to be converted into equality by subtracting the variable. That variable is known as surplus variable. Next, we have to see about the standard and canonical form of LPP. If you have any problem, first we have to formulate that LPP, and then we have to form a suitable form of the LPP, and then we have to find its solution. That form is known as canonical form and standard form. Two forms are used. First we have see the canonical form. The general linear programming problem can always be expressed in the following form, that is the objective function is of the form maximization type, not minimization type. Canonical form is objective function is maximization type, z equal to c1 x1 plus c2 x2 etc. cn xn, subject to the constraints. All constraints is of the form less than or equal to type. All the constraints is of the form less than or equal to, not equal to or greater than or equal to type. All the constraints must be less than or equal to type, under the non-negativity restriction x1 x2 etc. xn greater than or equal to 0. This form of LPP is called canonical form of LPP. Then This canonical form of LPP may be noted as matrix notation. Is as follows: maximize z equal to cx, objective function, subject to the constraint ax equal less than or equal to b and x greater than or equal to 0, non-negativity restriction, where c1 is, c means it is the constant, that is c1, c2, etc., cn. Here A is the n by n matrix, that is A11, A12, etc., A1n, AN, This is the n by n matrix. X is the non-negative variables, that is x1, x2, etc., xn. B is the right hand side variables, constant, right hand side constant, that is B1, B2, etc., Bm. Next, we have to know about the characteristics of canonical form. First, we note that the objective function is of maximization type, that is must be maximization type. If it is of minimization type, we have to convert this into maximization type by multiplying the objective function to -1. We convert into maximization type. Next, second point, all constraints are of less than or equal to type except for the non-negative restriction, that is constraints must be less than or equal to type. If it is greater than or equal to type, we have to convert into less than or equal to type by multiplying the constraint, that constraint to be -1 on both sides. For example, a11 x1 plus a12 x2 etc. a1n greater than or equal to bi is equivalent to, we have to multiply -1 on both sides. Therefore, that is we have get ai1 x1 minus ai2 x2 etc. minus ain xn less than or equal to minus bi. Suppose an inequality is equal to type, which is and equal to is equivalent to less than or equal to or greater than or equal to. We have considered this canonical form automatically less than or equal to type. Then third point, all variables must be non-negative. Suppose negative, unrestricted, negative means unrestricted sign is equivalent to, we have to convert into non-negative restriction by converting xj equal to xj dash minus xj double dash, that is where xj and xj double dash are non-negative, that is xj equal to xj minus xj dash minus xj double dash, where xj dash not equal, greater than or equal to 0 and xj double dash greater than or equal to 0. Next, we have to see about that standard form. In this standard form, that is the general form linear programming problem, is in the form maximize or minimization type. Standard form is any of the form. Objective function is any of the form, that is maximize or minimize. Is that equal to c1 x1 plus c2 x2 etc. cn xn subject to the constraints. Constraints must be equal to type, that is a11 x1 plus a12 x2 equal plus etc. a1n xn equal to b1, must be equality type constraints, and non-negativity restriction, that is x1 x2 etc. xn greater than or equal to 0 is known as standard form. Next, we see about the matrix notation of standard form, that is maximize or minimize z equal to cx subject to the constraints ax equal to b must be noted as, and x greater than or equal to 0 where c equal to c1 c2 etc. cn. A is the n by n matrix and x is the non-negativity variables, that is x1 x2 etc. xn. B is the b1 b2 right hand side constants b1 b2 etc. bm. Next, we see about the characteristics of standard form, that is first point is all the constraints is in the form of equation type except for non-negativity restriction. Then second point, the right hand side of each constraint is non-negative, that is b1 b2 bm must be non-negative. Third point, the inequalities can be changed into equation by introducing a non-negativity variable on the left hand side of such constraint. That is, if the inequality that is if it is less than or equal to constraint, we have to convert equality by introducing slack variable. If the inequality is of greater than or equal to type, we have to convert into equality type by introducing surplus variable. If, for example, suppose we consider the consider the constraint, that is x plus 2y less than or equal to 1 and 2x plus y greater than or equal to 1 and x comma y greater than or equal to 0 be the constraints of LPP. We have to convert into standard form. First one is less than or equal to type. We have to convert into equality type by introducing slack variable. Therefore, we get slack variable S1, that is x plus 2y plus S1 equal to 1. Second constraint is of greater than or equal to type. Therefore, we have to introduce surplus variable, that is 2x plus y minus S2 equal to 1, where x, y, S1, S2 greater than or equal to 0. We must note that slack and surplus variable must be greater than or equal to 0. Thank you.